Now we move on to the normal distribution, which is perhaps the most important distribution, and we will spend a fair amount of time on this. This is what a normal distribution looks like. It is sometimes called a bell-shaped distribution. We have a certain mean value denoted by mu, and the random variable is distributed around that mean value. A normal distribution is denoted using these symbols. So x is the random variable, n stands for the fact that this is a normal distribution. Any normal distribution can be defined based on the mean value or mu and the variance of that normal distribution. Knowing the variance is essentially the same as knowing the standard deviation. So if I say that x is a normal distribution with mean 10 and standard deviation of 2, i.e. variance of 2 squared, then we are completely defining a particular distribution. A normal distribution will have skewness of 0. That means that the distribution is completely symmetric. The amount of data to the left of the mean is exactly equal to the data to the right of the mean. In fact, the distribution to the left is essentially a mirror image of the distribution to the right. So that means that skewness is equal to 0. And something that you just need to memorize, kurtosis, which is a measure of how peaked the distribution is, and a measure of the tails is 3. So just by definition, the kurtosis of a normal distribution is 3. There is some basic information that you need to memorize related to a normal distribution, and I'll just share that with you over here. Approximately 68% of all distributions fall in the interval mu plus or minus 1 standard deviation. In the example that I just talked about, let's say that the mean or mu is 10. And if I said that the standard deviation is equal to 2, then what we are saying is that if the total area under this curve or total probability is equal to 1, then 68% of the data will fall within 1 standard deviation of the mean. 1 standard deviation is equal to 2 in this particular distribution. So 1 standard deviation will take us to 12 on the right side of the mean and 8 on the left side of the mean. So this total area is 68% of the total area under the curve. In other words, 68% of the data will lie between 8 and 12. So this is a continuous random variable which spans from minus infinity to plus infinity, and 68% of all this data will lie between 8 and 12. Approximately 95% of all observations fall in the interval mu plus or minus 2 sigma. Again, with sigma equal to 2, so 2 sigma gets us to 14 over here, and 10 minus 4, which is 6 over here. So we are saying that between 6 and 14, we now cover 95% of the data. And this is also fairly obvious looking at the picture, that if you have 100% of the data between minus infinity and plus infinity, then 95% of the data is covered if we go from 6, which is 2 standard deviations to the left of the mean, till 14, which is 2 standard deviations to the right of the mean. And finally, for this slide, approximately 99% of all data will fall within 3 standard deviations of the mean. Next, we move to the concept of confidence interval, and we will consider the same distribution with a mean of 10 and a standard deviation of 2. And what we are talking about here applies to any normal distribution. You might have another normal distribution with mean equal to 17 and standard deviation equal to 3.7. The same logic will apply. I'm just using 10 and 2 because the numbers are easy to work with. The 90% confidence interval for a given normal distribution is mu plus or minus 1.65 times the standard deviation. So if you have 10 over here, what this means is that 90% of the data will lie between 10 plus or minus 1.65 s. So if we do 1.65 times 2, we have 3.3. So what this means is the following. 90% of the data will fall between 13.3 and 6.7. 13.3 is 3.3 to the right of 10, which is essentially 1.65 times the standard deviation, and 6.7 is 1.65 standard deviation to the left of the mean. To give you a concrete example, let's say that you are evaluating a stock and the expected return on the stock is 10%, and you know that the standard deviation is 2. That's because the return is not necessarily going to be 10%. It is going to be distributed around 10%, and the distribution is depicted by 2. Given that you have this information and given that you treat the stock return as a normal distribution, what you can say to your boss is that you are 90% confident that the return will be between 6.7 and 13.3%. Similarly, you can say with 95% confidence that the returns will be between plus or minus 1.95 standard deviations of the mean. So this is a more precise number compared to 2, but approximately we can say that 95% of the data will be 10 plus or minus 2 times the standard deviation. So if the standard deviation is 2, we have 10 plus or minus 4. So 95% of the data will be between 14 and 6, and this is what we saw on the previous slide also. And finally, you can say with 99% confidence that the returns will be mu or 10% plus or minus 2.58 standard deviations. Notice that between this slide and the previous slide, here we are using slightly more precise numbers. So even though these also are approximations, but they are better approximations than what you saw on the previous slide. The single most important element to remember is this one. Even though you should also know the 90% number, you should also know the fact that one standard deviation from the mean, so plus or minus one standard deviation, gives you 68%. So these are basic numbers that you can look up from a table, which is what we'll discuss later, but it is important for you to memorize these core numbers. We now will talk about the standard normal distribution. For a standard normal distribution, the mean is 0 and the standard deviation is 1. So this mean, the central point is 0 and the standard deviation is equal to 1. The standard normal distribution, the random variable, is often denoted with the symbol z. So very often you will hear the term z value. That represents the random variable which is shown on the horizontal axis. You need to learn how to read the probability distribution table, and an excerpt is given over here. The probabilities given over here are cumulative probabilities for a standard normal distribution. Notice that they are calling this x or z. So generally you will see this denoted as a z value. A z value of 0 is this point over here. And notice that the cumulative distribution for a z value of 0 is 0.5. And this should make sense. Given that the distribution is symmetric, that means that half the data will be to the left of the mean. So the cumulative probability for a z value of 0 must be half of 1, which is 0.5. If you go to 0.1, then we are at this point. So with a z value equal to 0.1, clearly the cumulative probability is going to be a little more than 0.5, and that number is 0.5398, and so on. As the z value increases, we will have a higher cumulative probability. So that explains this column. What if the z value is 0.11? Then you use this number over here, and the cumulative probability would be 0.5438. So essentially this means that on the x-axis, if you are at 0.11, so that is your z value, then the cumulative probability is equal to 0.5438. So the first column and the first row essentially are used to come up with the z value, and then the data in the body of this table is essentially the cumulative probabilities. It is important to note that once you learn how to read the table, you should be able to use the fact that the distribution is symmetric. So in my simple example, if I ask what is the cumulative probability with z equal to 0.11, you simply come up with this number. What if I say that you need to come up with the cumulative probability for a z value of minus 0.1? Now clearly this number is less than, this probability is going to be less than 0.5, but over here you don't see any negative z values. So you use the fact that the distribution is symmetric. If you come to this point over here, which is 0.1, then you know that the cumulative probability up till 0.1 is equal to 0.5398, which means that the probability to the right of 0.1 is equal to 1 minus 0.5398, which is equal to 0.4602. Now this 0.4602 is the same as the probability to the left of minus 0.1 because the distribution is symmetric. So the answer to the original question being what is the cumulative probability for z equal to minus 0.1 is 0.4602. Next, we talk about transforming a normal distribution to a standard normal distribution, and you might wonder why this transformation needs to take place. Let us understand this through an example. Say the return on a stock is normally distributed with a mean of 10 and a standard deviation of 2. So you have a mean of 10 and a standard deviation of 2. What is the probability that the return will be less than 11%? So this is your 11% mark, and we need to find the probability that the return will be less than 11%. Now, unfortunately, we do not have a normal distribution table for every single mean and standard deviation. So what we need to do is transform this particular normal distribution. So the normal distribution with mean 10 and standard deviation 2 needs to be transformed into a normal distribution with mean 0 and standard deviation 1. Once we've done this transformation, then we can simply read probabilities of the table. To do the transformation, here is the formula that is needed. You have an x value, and that is what we have over here. For your normal distribution, the one that we are talking about here, the random variable is denoted by big X, and we want to find the probability that this big X is less than equal to 11. So let's do the transformation of this normal distribution into standard normal using this formula. The z value is equal to x minus mu divided by sigma. The transformation of the mean 10, so what does this become? If we plug into the formula, x over here is 10 minus the mean, which is 10, divided by 2. So 10 minus 10 is 0, divided by 2 is 0. So not surprisingly, the mean of 10 transforms to 0, and that is what we expect given the definition of the standard normal distribution. But the more interesting item is 11. So what does 11 transform to? 11 transforms to a z value of 11 minus 10 divided by 2. So this is 1 over 2, which is 0.5, which is essentially saying that 11% on the normal distribution transforms to 0.5 on the standard normal distribution. So the probability that the return is less than 11% is exactly the same that the probability on your standard normal distribution is less than 0.5. And this is something that we can look up on our table. If we go back to the table and we look at 0.5 as our z value, then the cumulative distribution is 0.6915. So for simplicity, let's say that this is 0.69. That means that the probability that the return will be less than 11% is 0.69. And if we are interested in the probability that the return is greater than 11%, then that is simply 1 minus 0.69, which would be 0.31. So hopefully this helps you understand why we need to do the transformation, and the formula that you must memorize is given right here. Let us look at a practice problem now. Assume that the annual earnings per share for a large sample of firms are normally distributed with a mean of 5 and standard deviation of 2. So let us draw that distribution here. We have a mean of 5 and standard deviation is equal to 2. What is the approximate probability of an observed EPS falling between 4 and 5? So what we are saying is the following. There is a certain probability that the EPS will fall between 4 and 5. So this is the probability that we are looking for, the shaded region. In order to solve this problem, we need to do a transformation. We need to transform this normal distribution into the standard normal distribution. 5 transforms to 0, and I will just write down the basic transformation formula. The z value is given by x minus the mean divided by the standard deviation. For a value of 5, you simply do 5 minus 5, which is also the mean, divided by the standard deviation. So that gives you 0, which is what we would expect. What about the 4? The 4 transforms to the following. The x value is 4. What is the corresponding z value? That is 4 minus the mean, which is 5, divided by the standard deviation, which is 2. So we have 4 minus 5 over 2, which is equal to 0.5. So this actually is minus 0.5. So we have minus 0.5 over here. Now we need to find this probability. What we know is that the total probability up till 0 is 0.5. So we need to subtract this probability from 0.5 in order to come up with the probability of being between minus 0.5 and 0. The probability to the left of 0.5 can be determined using the probability table. And again, we use the fact that the distribution is symmetric. If the table you are looking at doesn't have minus 0.5, you can find the cumulative probability for plus 0.5 and then subtract that from 1 to come up with this probability. And we have already done that. Earlier, we noticed that for 0.5, this whole area is 0.69, which means that this area is 0.31. So this area is 0.31, which means that this area over here, given symmetry, is also 0.31. And the area that we are after, which is right here, is equal to 0.5 minus 0.31, which is equal to 0.19. That 0.19 is the same as this area over here. So the probability that the EPS will be between 4 and 5 is equal to 0.19. What we have covered here might seem complicated if you've not seen this material before, but with sufficient practice you will realize that this is fairly mechanical and straightforward. Moving now to multivariate distribution. Multivariate simply means multiple variables. Let's say you have three random variables, A, B, and C, and each of these random variables is normally distributed. And if it helps you understand what we are talking about, say that these three random variables are the returns on three stocks A, B, and C. They are normally distributed. The mean for A is 10, let's say for B is 15, and C is 20. The standard deviation for A is equal to 4, B might be 9, and C, let's say, is 16. So if you combine these three stocks, and let's say that the weightage is equal, then can you come up with the overall mean for this portfolio and the variance for this portfolio? The answer is that yes, we can do that. And the fact that if each individual variable is normally distributed, then the overall portfolio's returns will also be normally distributed, and we can compute the mean or expected value for the portfolio as well as the variance for the portfolio, as long as we know all the means and we know all the variances or standard deviations, and we also need to know the pairwise correlations. So the correlation between A and B, B and C, and A and C. Notice that with three items in here, we need to have three pairwise correlations. In my simple example, n is 3. So if you look at this expression over here, we have 3 into 3 minus 1, which is 2, divided by 2, which is 3. So if you have three variables, then you need to have three pairwise correlations. If you happen to have four variables, say A, B, C, and D, then you would need to have 4 into 3 divided by 2, which is 6 pairwise correlations. And I'm sure you can do a quick analysis here and determine that 6 pairwise correlations will be necessary. So that is all that you really need to know with regards to multivariate distribution.